Dear students, welcome to this digital lecture series. Today we are going to see another interesting topic in relativity, and it is time dilation. So what does time dilation means? To understand this, we have to see two important concepts in relativity. First is the proper time. The time or the time interval of an event as measured in the frame of reference where the event has actually taken place is called the proper time. It is generally denoted by T0. And another concept is apparent time. If an event takes place in one frame of reference, which may be in motion or at rest, then the time or the time interval of the same event as measured by an observer who may be at rest or in motion from any other frame of reference, it is called the apparent time. And the apparent time is generally denoted by T, capital T. Now let's try to understand it in a more detailed manner. Suppose that an event occurs in frame of reference S, and there is another frame of reference S dash which is moving. Now the time or the time interval of the event which is measured in the frame S where the event has occurred or taken place, that time will be called proper time. It is denoted by T0. And the time interval, if it is measured from another frame of reference, in our example we have taken S and S dash. Event has occurred in frame S. So if somebody is measuring that event time or time interval of that event in the frame S dash, then that time will be the apparent time. So just remember, the frame of reference where an event occurs, and if you are measuring the time in that frame of reference where the event has occurred, then that is the proper time. And if you are measuring the time of that event from any other frame of reference, then that will be apparent time. So with this knowledge, let us see what is time dilation. The simple statement of time dilation is that a clock moving with relativistic speed with respect to a stationary observer always appear to go slow. Or the same statement can be put in other words, that the apparent time interval of an event as measured by a moving clock or an observer is always more than the proper time interval of the same event measured by a stationary observer. Just remember, according to time dilation, the apparent time interval of an event is always greater than the proper time interval of the same event. Now this is called time dilation, and time dilation is a reciprocal phenomena. As we progress in this lecture, we will see later on what does it mean that a time dilation is a reciprocal phenomena. Now consider two frame of references S and S dash. Let S be stationary and the frame S dash be moving with a velocity v along the positive x-axis with respect to the stationary frame S. Now let an event occur in the stationary frame of reference S at an point whose x coordinate is suppose x. Now let t1 be the time of beginning of the event and t2 be the time of end of the event, and note that the time t1 and t2 are measured simultaneously at the same time. Then the proper time interval t0 of the event in stationary frame S is given by t0 is equal to t2 minus t1, end time minus the beginning time. And why this t0 in the frame S is a proper time? Because the event has occurred or taken place in the frame of reference S. Now if the same event is observed from the moving frame of reference S dash, and suppose that t1 dash and t2 dash are the time of beginning of the event and the time of end of the same event, but it is measured from frame S dash. Now in this case, the difference t2 dash minus t1 dash, it gives the time interval of an event which is measured in another frame of reference. Note that the event has taken place in frame S. So time in frame S will be proper time. And the time interval which we are measuring in the frame S dash, that will be the apparent time. So the apparent time interval T of the same event which is measured in the frame S dash, which is a moving frame, it will be given by T is equal to T2 dash minus T1 dash. This is our equation 2. But we know that by Lorentz transformation, the time interval T dash in a moving frame is given by T dash is equal to beta times T minus Vx divided by C square, where beta is equal to 1 upon under root of 1 minus V square upon C square. Now here this x, it denotes the x coordinate of the point where the event has taken place. Therefore, now on the same logic, if we write T2 dash, then we can write T2 dash is equal to beta times T2 minus Vx upon C square, and T1 dash is equal to beta times T1 minus Vx upon C square. Now I should have written in T2 dash I should have taken x2, and in T1 dash I should have taken x1, but I have used x. Why? Because x1 is equal to x2 and that is equal to x, and that is the x coordinate of the point where the event has taken place. So it is same, x1 is equal to x2 and I have taken it to be x. That is why in this equation here I have used, instead of x2 I am using x, here instead of x1 I am using x. So if I put these values in equation 2, I get the apparent time t is equal to t2 dash minus t1 dash, and that is equal to beta times t2 minus vx upon c square minus beta times t1 minus vx upon c square. So just observe it here that this minus vx will get cancelled with this plus vx upon c square. Minus minus gives plus. So I get t is equal to beta times t2 minus t1. But what was t2 minus t1? It was our proper time interval t0. So t is equal to beta times t0, where t is the apparent time interval and t0 is the proper time interval. So if I substitute the value of beta, then I get apparent time t is equal to t0 divided by under root of 1 minus v square upon c square, and that is our equation 3. So if you observe this equation, just observe this equation, if I put any value of v here, this denominator always becomes less than 1. And if the denominator is less than 1, t upon the denominator which is less than 1 gives me the value of t, apparent time t, and this t will be always greater than t0. So what is our conclusion? Therefore, we notice that the apparent time t, it is always greater than the proper time t0. Thus, apparent time is always greater than the proper time. And this is the consequence of the special theory of relativity. So, in this derivation, we had considered that the event occurs at a point x in the stationary frame of reference S, where the proper time was measured and it was t0, and the apparent time t was measured in the frame S dash, which is moving with a velocity v along the positive x-axis with respect to the frame S, which was a stationary frame. Now let us see what happens if we consider that the event occurs at a point x, at a point having the x coordinate x dash. And where is this point? In the frame of reference S dash, moving with a velocity v along the positive x-axis. In the previous case, the event had occurred in the stationary frame S, and we have found that apparent time t is greater than proper time t0. Now we are just going to see what happens if we take the case that the event has taken place in the frame S dash at a point whose x coordinate is x dash. Now let the clock placed in the frame S dash measure the time of an event as t1 dash and t2 dash, where t1 dash is the time for beginning of the event and t2 dash is the time for end of the event, but where? In the frame of reference S dash. Our event we are taking into consideration in this case that the event is occurring in the frame S dash. So the time interval which is measured now in the frame S dash, that will be our proper time. Just remember the definition of proper time. It is the time or the time interval of an event which is measured in the frame of reference where the event has taken place. In the second case, our event is occurring in the frame of reference S dash, the time of beginning and end of the event are t1 dash and t2 dash. Therefore, the proper time t0 in this case, it will be the time which is measured in the frame s dash, and that is t0 is equal to t2 dash minus t1 dash. Now, a clock which is placed in the frame S observes and measures the time of the same event, and let T1 be the time of beginning of the event, T2 be the time of end of the event, but in the another frame, that is the S frame of reference. Now the frame S is in a relative motion with velocity minus v with respect to frame S dash. Just see here, the frame S dash is moving with a velocity v along positive x-axis, and the frame S was stationary. Now this is equivalent. If we consider the relative motion and if we observe from the frame S dash, then an observer in the frame S dash will notice that the frame S is moving in an opposite direction with the same velocity. Note that the frame S dash is moving with a velocity v along positive x-axis and S is stationary. But for an observer in frame S dash, he will have an feeling that he is stationary in the frame S dash and the frame S is moving in the opposite direction, that is in a negative x-axis direction, but with the same velocity v. This is because we have considered the relative motion between S and S dash. So, then the apparent time in this case of an event which is measured in the frame S, it is given by t is equal to t2 minus t1. Now, by the Lorentz inverse transformations, we can write t1 is equal to beta times t1 dash plus vx dash upon c square. t2 is equal to beta times t2 dash plus vx dash upon c square. Now, how have we written these equations? If t dash is equal to beta times t minus vx upon c square is the Lorentz transformation, then the inverse transformation, Lorentz inverse transformation, can be obtained just by changing the minus sign into plus and by interchanging the primed quantities with non-primed. Means instead of t, we have to write t dash. So instead of t1 dash, I have to write here t1. Change the minus sign with plus, and this x is changed by x dash. And here it was t, which I have changed with t dash. So I get t1 is equal to beta times t1 dash plus vx dash upon c square, and t2 is equal to beta times t2 dash plus vx dash upon c square. If we put these in equation 4, then we get the apparent time t is equal to beta times t2 dash plus vx dash upon c square minus beta times t1 dash plus vx dash upon c square. This plus vx dash upon c square gets cancelled with this minus vx dash upon c square. So apparent time t is equal to beta times t2 dash minus t1 dash. And remember that in second case, this t2 dash minus t1 dash, it gives the proper time t0. So finally we can conclude that the apparent time t is equal to t0 upon under root of 1 minus v square upon c square. In the second case, and this is our equation 5. So from equation 5, once again we observe that the apparent time t is greater than the proper time t0. So this is called the time dilation. Now if you take the first case, the event has occurred in the frame S, which was stationary, and apparent time was measured in the frame S dash, which was moving, and we have found that apparent time is greater than the proper time. In second case, the event has taken place in the frame S dash, which is moving, and the apparent time was measured in the frame S, which was stationary, and in this case also we have noticed that the apparent time is greater than proper time. So if we interchange the frame of references, still the time dilation, it holds true. The apparent time is always observed to be greater than the proper time, and therefore it is said that the time dilation is a reciprocal phenomena. Now, based on this time dilation, we can prove that a clock which is moving, it ticks slowly, means a moving clock appears to go slow. It will go slow. So just see how we can do this. Suppose that the frame S dash moves with a velocity v with respect to a stationary frame S along the positive x-axis. Let an event occurs in the frame S dash. Then the clock which is present in the frame S dash, it will note a particular time, and that time which is measured in the frame S dash, it will be proper time, and it is given by t0. The event has occurred in the frame S dash, so the time interval of the event measured in the frame S dash, it will give the proper time denoted by t0. So the time interval of the same event which is measured in the another frame, that is S, say suppose it is the frame S, that will be called the apparent time, and it is denoted by time t. If we proceed in the same manner, then according to time dilation, the relation between apparent time and the proper time will be apparent time t is equal to proper time t0 divided by under root of 1 minus v square upon c square. So if you observe this equation, the denominator is always less than 1. Therefore, the apparent time is always greater than the proper time t0. And where was this proper time measured? In the frame S dash, where the event has taken place. Apparent time was measured in the stationary frame S. So what can we conclude? That the clock which is present in the moving frame S dash, which had measured the proper time t0, that proper time t0 is less than the apparent time t. This means the clock in a moving frame S dash measures a smaller time for an event as compared to the time measured for the same event by a clock which is in a stationary frame S. In short, a moving clock has measured the time interval, this proper time interval, which is less than the time interval, that is apparent time, measured by a stationary clock. Means the moving clock has measured a smaller time for the same event as compared to a stationary clock. Therefore, we can conclude that the moving clock appears to go slow or the moving clock ticks slowly. This is the consequence of time dilation in relativity. So now this is an example. Suppose that a person is going in this rocket and clock in the rocket, since the rocket is moving, the clock is also assumed to be moving, and this is a person on the earth, he is stationary. In time dilation, we have seen that the time measured by a moving object is less than a time measured by a stationary object. So the time measured by this moving clock is small. Goes in a less slower time as compared to this clock which is stationary. So a moving clock is slower as compared to a stationary clock, or moving clock goes slow as compared to the stationary clock. Now this can also be seen from this particular slide. Here, event has occurred in a rocket. So the time measured by this clock in the rocket will be a proper time, and time measured by the person on the earth, it will be a apparent time. So proper time which is measured in this rocket for the event which has taken place in the rocket, it is less as compared to the time measured by for the same event by a stationary observer. And see again, here is a visualization of this. Just observe these two clocks and the speed of movement of the rocket. This is time shown by the rocket. This is proper time. And this is the time shown by the stationary observer. In every case, see now the speed is 0.076 c. In this case, the time shown by the earth observer is more as compared to rocket observer. Now the time is 0.833 c. Just observe the difference. Observe which clock is going in a greater speed. You will see that moving clock means the clock in the rocket, it shows less time, while the clock on the earth, which is stationary, it shows larger time or greater time. Thus our final conclusion is that a moving clock always appears to go slow, or it ticks slowly as compared to the stationary clock. So that's all about time dilation. Have a nice day.